Geologists have a saying, rocks remember. That was Isaac Asimov. And today, we're going to try and listen really closely to what the rocks are telling us deep down beneath the ocean. Okay, let's unpack this. We're diving into something, well, huge, powerful, and really critical if you live anywhere near the Pacific coast, the Cascadia Subduction Zone. It's a major topic. Important for earth science, sure, but also for safety, for planning.
Absolutely. And to get the scale, you really have to picture these two massive tectonic plates, like continent-sized puzzle pieces of the Earth's shell grinding against each other miles underwater. A subduction zone, that's just where one plate is being shoved, forced under the other one. And the Cascadia one, it runs all the way along the Pacific Northwest, Northern California, Oregon, Washington, right up to British Columbia. It's where this smaller plate, the Honda Fuca plate, dives under North America. And yeah, that makes it one of the most active and, frankly, dangerous spots on the planet.
Dangerous. Because they don't just slide smoothly, right? They get stuck, locked together. And that builds up incredible stress over, well, centuries. This happens along what's called a megathrust fault, basically that boundary line between the two plates. And when that locked part finally lets go, bang, all that stored energy releases as a massive earthquake.
And the movement itself is tiny each year, like fingernail width maybe. But over hundreds of years, that pressure builds and builds. We're talking potential earthquakes strong enough to wreck cities hundreds of miles away and generate tsunamis. Huge waves, tens, maybe even 100 feet high, hitting the coast. Think about the energy scale. A full rupture, the whole length letting go, it could release more energy than like all human activity uses in an entire year. It's almost hard to grasp.
And we know this isn't just theory. The rocks do remember. The geology, the sediments, combined with indigenous oral histories, they tell us these huge events have happened before. Looking back, the evidence points to giant quakes roughly every 500 years, give or take maybe a couple hundred.
Yeah, that's the average spacing, roughly.
And the last really big one, January 26, 1700. Imagine that. Way before, Seattle or Vancouver were cities. We know about it from clues like drowned forests and tree rings, coastal marshes that suddenly dropped, and critically, from indigenous knowledge. Stories passed down about the shaking, the land falling, and those devastating waves.
Those oral traditions are incredibly valuable scientific data points, really.
So given that history and the sheer scale of the threat, the big question for scientists has been, okay, the next time it goes, will it be the whole fault line rupturing at once, like 1700? Or could it break in smaller pieces, like segments? Because that difference is, well, it's huge. It's the difference between a terrible disaster and an absolutely catastrophic one hitting multiple states and Canada all at once.
Exactly. That's the key question. And it's what this new research we're looking at today really tried to get at. So this deep dive, we're pulling info from earth.com, which references a big study published in Science Advances, a top journal. And this study, it gives us the most detailed picture yet of what that fault boundary actually looks like, miles down.
Okay, so how do you even see something that's miles offshore and 6 miles deep?
Yeah.
The source mentioned a specific expedition.
Yeah, it was quite the effort. A 41-day trip back in summer 2021. They used this research ship, the Marcus G. Langseth, and it basically sailed back and forth, crisscrossing the whole Cascadia Zone, towing this array of very powerful acoustic gear behind it.
Acoustic. So using sound waves.
Yeah.
Like sonar, but way more powerful.
Exactly. But really low-frequency sound.
Yeah.
Designed to punch right through all that rock and sediment down to the plate boundary itself. The sound waves bounce back off different layers, different structures, and the instruments record those echoes. And by processing all that data, they can build these incredibly detailed 3D images, like a CCAT scan of the Earth's crust.
Wow, geological ultrasound, yeah. So what did these new high-def pictures show? The lead scientist, Suzanne Carbot, she's quoted in the source.
Yeah.
Sounds like it was pretty eye-opening.
Oh, definitely. She points out, the models currently in use by public agencies were based on a limited set of old, low-quality 1980s-era data. Think about that. The baseline was kind of fuzzy. And the new data, quoting her again, shows the megathrust has a much more complex geometry than previously assumed. She says this study provides a new framework for earthquake and tsunami hazard assessment. Big words.
Okay, complex geometry. What does that actually mean down there? It's not just one clean break.
That's the main takeaway. It's definitely not just one smooth, continuous fault surface. Instead, it looks more like distinct segments lined up next to each other. They identified at least 4 clear segments, maybe more. And these segments seem to be separated by other smaller faults buried down there, cutting sort of crosswise towards the coast.
Huh. So like sections along the main fault.
Kind of like that, yeah. Imagine the main fault is a long zipper, but it has these internal dividing lines running across it.
That's really interesting. So finding these segments, these dividers, what's the big implication? Does it mean the whole thing is maybe less likely to unzip all at once?
Well, that's the multi-billion-dollar question, isn't it? The data shows each segment is a bit different. Different slopes, different amounts of sediment piled on top, maybe different cracking patterns in the rock. And those differences could affect how a rupture moves. Those crosswise faults, the dividers, they could act like speed bumps or walls, maybe stopping a rupture from spreading along the whole length. But, and this is the crucial but, there's also the chance those barriers could fail. And if they fail, the rupture could just keep going, jumping from one segment to the next in one enormous earthquake.
Ah, okay. So it adds complexity, possibility of smaller breaks, but doesn't rule out the big one.
Precisely. Harold Tobin, one of the co-authors, he put it well. He said, basically, we can't say only single segments will rupture, or that definitely the whole thing will go. But this does upgrade evidence that there are segmented ruptures. So the idea of it breaking in pieces just got stronger evidence.
Got it. And the sources also zoom in on one specific segment. They call it a wild card. Where's that, and what makes it stand out?
Right. This segment runs from about southern Vancouver Island down towards the mouth of the Columbia River near Astoria, Oregon. It's the wild card because these new images show the contact surface there where the plates meet is remarkably smooth.
Smooth. As in, less friction.
Exactly. Think polished glass versus, rough concrete. Less friction means fewer natural sticking points or barriers to slow down a rupture once it starts. Stress could potentially travel much further along this smooth stretch before it runs into something that might stop it. And the modeling they did, using this new smooth geometry, it suggests that if just this one segment ruptured completely, it could actually increase the shaking intensity by one whole unit on the modified Mercalli scale across a big area, including places like Puget Sound, Seattle, Tacoma.
Wait, 1 unit higher on the Mercalli scale?
Yeah.
That measures the effects we feel, right? Damage to buildings, how it feels to people. So that's a really significant jump in impact.
It is. It's a noticeable, potentially much more damaging level of shaking on the ground. And there's another worry with this segment. The fault boundary here also dips down under North America at a relatively shallow angle.
Shallow, meaning?
Meaning the locked part of the fault, the part building stress, extends further inland. It might actually go underneath the Olympic Peninsula, getting closer to those big cities like Seattle and Tacoma. That geometry, shallower and smoother, could mean the huge movement offshore translates more efficiently into stronger shaking right where lots of people live.
Okay, that's sobering. When you hear about that kind of potential, you naturally think, have we seen something like this play out elsewhere? The sources mentioned Japan, 2011.
Yes, the Tohoku earthquake and tsunami on March 11, 2011. It's a terrible but important parallel. That was also a massive megathrust earthquake. Japan had prepared extensively. They had seawalls, building codes, but they're largely based on models that, underestimated how large a rupture could be on that specific part of the fault. The tsunami that hit was just bigger than anticipated. It overwhelmed defenses, caused immense destruction, and led to the Fukushima nuclear disaster. It really showed how even well-prepared nations can be caught out by an underappreciated segment, behaving unexpectedly, or just the sheer scale of these events.
A hard lesson.
A very hard lesson. And another thing from Japan, it wasn't just the quake and tsunami, it was the cascading failures afterwards. Power grids down, roads flooded, blocking help, chemical spills. All these interconnected systems failing made the human toll so much worse long after the shaking stopped. It's a complex disaster, not just one thing.
So taking those lessons and now armed with these much better maps of Cascadia, what does this mean for preparedness on the West Coast now? How does this new data actually help?
It's incredibly valuable. Emergency managers, engineers, they now have a much clearer picture of the fault's complex shape. This lets them run much more sophisticated computer simulations. They can test critical things, bridges, hospitals, highways, power lines, against more realistic shaking patterns. They can model different scenarios. What if just segment A goes? What if B and C go? What if the whole thing goes? How does the shaking differ? Where are the waves highest? And those simulation results, they feed directly into things like updating building codes. How strong do new buildings need to be? Which older ones need urgent retrofitting? It also helps fine-tune the earthquake early warning systems being rolled out in the Pacific Northwest systems like Shake Alert. Better models mean potentially more accurate warnings.
Giving people those crucial seconds or tens of seconds.
Exactly. But it's also important to note this is still ongoing work. especially translating these detailed seafloor maps into precise tsunami forecasts. That's still, as one scientist put it, a work in progress. The sources mention Kellen Wang from the Geological Survey of Canada. His team is using these new fault details to model exactly how the seabed might suddenly lift up or drop down during different types of quakes. Then another group takes that seabed movement data and plugs it into tsunami models to predict wave heights and arrival times more accurately along the coast.
Okay, so the science is filtering down, and that leads to practical things like evacuation routes.
Absolutely. This improved understanding helps emergency managers refine those tsunami evacuation route maps you see on posts in coastal towns from, say, Brookings, Oregon, all the way up to Port Alberni on Vancouver Island. Many of those towns already run evacuation drills, often timed with the monthly siren tests. This new science helps make sure those plans are based on the best possible understanding of the risk.
It really drives home that, okay, we can't predict the day it will happen, but understanding the probabilities and the potential impacts much better. That lets us make smarter decisions now. Decisions like where to prioritize building those vertical evacuation structures in low-lying areas, which schools need seismic upgrades first, which highway sections are most vital to keep open.
Yeah, it guides resource allocation.
And for you, the listener, especially if you're in this region, knowing the risk is the first step to being prepared. The sources tick off some key individual actions. Things you can do today, like strap your water heater down. Seriously, secure heavy furniture, build that emergency kit food, water, first aid, meds for a few days, maybe even a week. And know the difference. An earthquake alert on your phone means drop, cover, hold on now. A tsunami siren after shaking stops. That means get to high ground or inland immediately. Don't wait.
Yeah, treating preparedness as just a normal chore, part of living here, rather than some distant fear, that really helps communities and individuals be more resilient, better able to bounce back when those locked plates finally do slip.
So we've covered a lot here. The complex, segmented nature of the Cascadia megathrust revealed by this amazing new data. The stronger evidence now for ruptures happening in segments, not just all at once. That concerning wildcard segment, smoother, shallower, potentially closer impact to cities. The vital lessons from places like Japan in 2011. And how all this science is actively refining hazard maps, building codes, early warning, and evacuation plans.
It's a huge leap in understanding.
For anyone tracking current events, natural hazards, or just how science informs safety, this is pretty critical stuff.
And maybe a final thought to leave you with. Just reflecting on how dynamic our planet is. We're always learning, always developing new tools to listen to the Earth, to understand its complexities. This ongoing scientific quest, it's not just academic, it directly impacts lives, how we prepare, how we respond. Being informed about these powerful natural forces isn't just interesting knowledge. It's really a fundamental part of being a prepared citizen.
So, what stands out to you from this deep dive on the Cascadia threat? Remember, this deep dive drew from reportingonearth.com based on a full study published in the journal Science Advances. If you found this valuable, if you want to stay informed on topics like this, please do take a second to like and subscribe. And leave us a comment. What questions do you still have? What other topics, earth science hazards, current events should we tackle in a future deep dive? Let us know. Thanks for joining us for this deep dive into the Cascadia threat. We'll catch you on the next one.